In lesson 4.6, you will perform operations with complex numbers. In this first example, we want to solve 2x squared plus 26 equals negative 10 for x. So since there's no x term, we can use our square root method and get x squared alone. To get x squared alone, I'm going to start by subtracting 26 from both sides. That'll get my x squared term alone, and I'll have negative 36 on the right. Okay, now I'm going to divide both sides by 2 so that I have just x squared on the left. And simplifying on the right, negative 36 divided by 2 is negative 18. And now I need to undo the power to get just x, so I'll take the square root of both sides. The square root of x squared is x, and remember we get two solutions whenever we take the square root of our variable squared. And I need to simplify the square root of negative 18, but we know in our real number system we can't take the square root of a negative because there's no number that I can multiply to itself to give me the product negative 18. I would always get a positive product. So what I have here is an imaginary number, and I'm going to simplify that imaginary number by factoring negative 18. The perfect square factor in 18 is 9. So I'm going to factor 18 into 9 times 2, but then I have that factor of negative 1 also, which is our imaginary number. So simplifying again using our product property of square roots, I can take the square root of 9, that's 3. I can take the square root of negative 1, that's I, my imaginary number, and I've got the square root of 2 as a factor also. So that's our solutions, our imaginary solutions to this quadratic equation. Negative 3i times the square root of 2 and positive 3i times the square root of 2. Here we want to add or subtract complex numbers. A complex number has a real number part and an imaginary part. When we subtract these two complex numbers, we're just going to distribute and add like terms like we would for binomials in our real number system. So this is a positive quantity, and when I distribute through by positive 1, I won't change the sign of those terms. In the second quantity, I'm going to distribute through by negative 1. So negative 1 times 3 is going to give me negative 3, and negative 1 times negative 7i is positive 7i. And now adding like terms, my real number parts are 2 and negative 3, so I get negative 1, and my imaginary parts are negative 3i and positive 7i, so I'm going to get positive 4i altogether. So that difference is a complex number in a plus bi form. The second example, let's distribute again. To get rid of parentheses, negative 1 times 3 is negative 3, and negative 1 times I is negative I. Positive 1 times 2 is positive 2, and positive 1 times negative 3i is negative 3i. Okay, adding my like terms again, my real number parts are negative 3 and 2, so I'm getting negative 1. And then 2i minus 1i is 1i, and 1i minus 3i is negative 2i. So again, that difference in sum is a complex number, negative 1 minus 2i. Now over here we're going to graph those complex numbers on the complex number plane. The horizontal axis is the real axis, and the vertical axis is the imaginary axis. And to graph a complex number like negative 1 plus 4i, I would start at the origin, and I would go 1 unit to the left along the real number axis, and then 4 units up parallel to the imaginary axis. And I'll just label that negative 1 plus 4i. Okay, graph the second complex number here that we got as a solution. negative 1 minus 2i. So again, I'll start at the origin. I'll go 1 unit to the left and 2 units down. This is negative 1 minus 2i. In these three examples, we will multiply complex numbers, and we'll multiply by distributing and adding like terms, just like we do in the real number system with our polynomials. So negative 1 times 3 is going to give us negative I times 3 is going to give us negative 3i, and negative I times positive I is negative I squared. Now I have to leave this product in a plus bi form, and so I have to get rid of this I squared. I squared is equal to negative 1, so all I have to do is replace I squared with negative 1 and simplify. That's going to be my real number part. So I'll do that first. Negative times the negative 1 is positive 1 minus 3i. And that's a plus bi form. Distributing again, 2 times negative 6 is negative 12. 2 times negative 2i is negative 4i. And starting over with 3i times negative 6 is negative 18i. 3i times negative 2i is negative 6i squared. So again, I'll simplify negative 12, and then I'll add my I terms in the middle. Negative 4i and negative 18i is going to be a total of negative 22i. And minus 6 is multiplied to I squared, which is negative 1. So negative 6 times negative 1 is positive 6 added to negative 12. I have negative 6 for a real number part and minus 22i for an imaginary part to this complex number. Okay, let's distribute again. 1 times 1 is 1. 1 times negative 2i is negative 2i. Starting over, 2i times 1 is positive 2i. And positive 2i times negative 2i is negative 4i squared. So, simplifying and adding like terms in the middle, negative 2i and positive 2i are going to sum to 0, so I have no middle term or I term, and I'm going to replace that I squared with negative 1. So I have negative 4 times negative 1, which is positive 4 plus 1, so the whole thing simplifies to 5. This is the case where we're multiplying conjugates. 1 plus 2i times 1 minus 2i, those are conjugates, and when we multiply conjugates together in the complex number system, we get a real number, a real rational number. Okay, we're going to use conjugates to divide complex numbers because we want to leave this quotient in a plus bi form. So we're going to multiply by the conjugate of the denominator over itself. 1 minus I over itself is the form of 1 that we're going to use to multiply to this quotient. So we're going to do the distributing on the top and the bottom and simplify. So I'll distribute on the top. 2 times 1 is 2. 2 times negative I is negative 2i. Negative 7i times 1 is negative 7i. And negative 7i times negative I is positive 7i squared. Okay, on the bottom, distributing, 1 times 1 is 1. 1 times negative I is negative I. I times 1 is positive I. And I times negative I is negative I squared. So again, simplifying, negative 2i and negative 7i is a total of negative 9i. And then I have 7 times negative 1. I squared is equal to negative 1. On the bottom, I have 1, and I have negative I plus positive I, that's 0. And I have a minus 1. So on the top, 7 times negative 1 is negative 7 added to 2. That's negative 5. minus 9i. And on the bottom, negative times a negative 1 is 1. 1 plus 1 is 2. But I don't leave my result in this form because I want it in a plus bi form, so I need to divide both negative 5 by 2 and negative 9 by 2 in order to leave this answer in a plus bi form. I need to see the real number part and I need to see the imaginary part. Okay, in our last example, we're going to determine which complex number is closer to the origin on the complex number plane. So to do that, we'll use the absolute value of a complex number. It's the distance from the origin on the complex number plane. So all we have to do if we want the absolute value of negative 2 plus 5i is use this formula for distance or absolute value. So we'll take the square root of a squared plus b squared, and our a value is negative 2, and our b value is 5. So underneath this radical, we've got 4 plus 25, or the square root of 29. Okay, the next one, we're going to find the distance from 0, so we'll take the absolute value of 5 minus I, which is equal to the square root of a squared plus b squared, and our a value is 5, and our b value is negative 1. So this time underneath the radical we have 25 plus 1, or the square root of 26. Okay, and the last one, the absolute value of negative 6i is the square root of a squared plus b squared. Our a value is 0, and our b value is negative 6. So this time under the radical we have a perfect square. We have 36, and the square root of 36 is 6. So now comparing these radicals, I know that the square root of 26, using my calculator, is approximately 5.1, and the square root of 29 is approximately 5.4. And the question asked was determine which complex number is closer to the origin on the complex number plane, so that would be 5 minus I is the closest to the origin on the complex number plane, and negative 6i is the furthest from the origin on the complex number plane. Include with your notes of this video guided practice problems 1 through 17 odd, found on pages 275 to 279 of your textbook.